Okay, Harold and Maude have gone into business together. Apparently, Harold looked up his old friend Maude after years of separation, and he was so touched that she had named her favorite pig after him that they became great friends again and they've gone into business. And they are manufacturing these cylindrical containers. And they're manufacturing them for government specifications, so they have to contain 1,000 cubic centimeters of liquid. That's what they're trying to do, manufacture cylindrical containers that contain this amount of liquid. Now, being smart business people, this is Harold and Maude, so okay, but they're going to get this one right. They're going to realize that they can minimize their costs if it's going to require less material to use this. So they've decided their goal is to minimize the amount of material needed to build one of these things, which basically means minimize the surface area. That would be the amount of material required to build this cylindrical container. Okay. So our task is to find the dimensions that do this. Okay. Now, of course, if this is a cylinder, the dimensions are going to be just the radius of the base and the height of the cylinder. Okay. So this is my goal. I'm going to actually, before I even get an equation for that, I'm going to just ask what my constraint is. What's going to keep me from just making a really small one? And the constraint is that I have to contain 1,000 cubic centimeters. So my constraint is actually that the volume must equal 1,000. Okay. Okay, so let's take a look. The volume, I remember my formula for that. That's just area of the base times the height. So that's going to be pi r squared times the height is equal to 1,000. Okay, that's my constraint. The thing I want to minimize is the surface area. Now the surface area is going to consist of three different parts. I'm going to have the top surface, the bottom surface, and then I'm also going to have the sides of that cylinder. And the sides of that cylinder, I can sort of imagine that it's like I've got a soup can with the label. I can unwrap that. Okay, so we're going to get a cylinder. Sorry, we're going to get a rectangle. So this side would correspond to the height of the cylinder. The other side corresponds to the circumference of the cylinder. Okay. So this is going to have dimensions of h, and then 2 pi r is the circumference of that, that cylinder. Okay, so the top and the bottom, of course, are just the area of that disk. So that's going to be a pi r squared and a pi r squared. So the thing I want to maximize is the surface area, which is going to be 2 pi r squared plus 2 pi r h. Okay, that's the thing I want to maximize. Minimize. Okay, my constraint, the thing I don't have any control over, is that pi r squared h has to equal 1,000. Now, just like our last problem, the difficulty that we have is that area right now is a function of two variables, r and h. We only know how to work with functions of one variable. Okay. So I'm going to take this and I'm going to solve, and it looks like it's easier to solve for h. So I'm going to say h is 1,000 over pi r squared. Once I have that, I can go ahead and plug in to my formula for the surface area. So if I do that, my area is 2 pi r squared plus 2 pi r times for h, I'm plugging in 1,000 over pi r squared. Now, I can simplify that a little bit. So the area is 2 pi r squared. I can cancel a pi, and I can cancel a factor of r, but that's going to give me plus 2,000 over r. And I probably want to rewrite that, because I know I'm going to be taking derivatives, as 2,000 r to the negative 1. So now I've expressed my area as a function of one variable r. Now I want to state my domain. I have to wait until I've decided which variable I'm keeping, because my domain is going to be the values that r can take on, and the values that r can take on are probably different from the values that h can take on. So you do need to wait until you know which variable you're working with before you describe the domain. Okay. Now, again, the domain is going to just be an interval from the smallest that r could be to the biggest that r could be, and any dimension, always the smallest that it could be, is 0. In this case, though, I can't include that, because I need my constraint to be true, and if r was 0, the volume would not be 1,000. Okay. So in the last example we did, we had the option of including the endpoint as a degenerate case, because we could still technically make the constraint equation true. Here, because the constraint equation involves multiplication, I cannot include the case that r is 0, because that would just kill off all the volume. Okay. Now, if I want to look for what the biggest r could be is, that's going to correspond to making h as small as possible, right? If I shrink the height, I've got to make a bigger base in order to keep the volume the same. Now, h, the smallest h could be a 0, except that, of course, it can't be, because then this wouldn't be true. But if h were to go to 0, r would have to go to infinity. So our domain is this open interval. R just has to be a positive number. Now, since we're working on an open interval, the extreme value theorem doesn't apply. So, I don't know for sure that a minimum value exists. Now, there's a nifty trick that we're going to see in this one, but let's just keep in mind going into this problem that it's very different from the last problem. The last time we knew there was a max, and we just had to find it. Now we have to find out if there's a min, and if so, find it. Okay, so I'm going to look for critical points, because that's the only place where this could be. So a prime would be 2 pi r minus 2,000 r to the negative 2. Notice that's 2 pi r minus 2,000 over r squared. Okay. That is always defined on our domain. It's undefined at 0, but 0 wasn't in the domain. So any critical numbers I have are going to be when this is equal to 0. So if 0 is equal to 2 pi r minus 2,000 over r squared, if I've just got two terms and their difference is 0, I'm just going to add this one over. So I'm going to get 2,000 over r squared equals 2 pi r. Can multiply that r squared over to the other side. So 2,000 is equal to 2 pi r cubed. Let's come up here. R cubed is going to equal 2,000 divided by 2 pi, which is 1,000 divided by pi. And so r would just be the cube root of 1,000 pi's. All right, that is a positive number, so it is in our domain. Now, what I'm going to do is I'm going to draw a number line, because that's how I would check for maxes and mins in general. And I'm going to use the shape of the graph to see whether this actually corresponds to a min. Okay. So I'm going to mark off the cube root of 1,000 over pi. I need to test some numbers. So I'm going to try plugging in 1. Notice I'm only allowed to plug in positive numbers. In theory, negative numbers are in the mathematical domain of this function, but they're not in the practical domain for this problem. Okay, if I plug in 1, oh dear, my derivative, I shouldn't have erased it, was 2 pi r minus 2,000 over r squared. Notice if I plug in 1, this is going to become just 2 pi minus 2,000. The negative piece dominates, and this is negative. Okay. Now, I need to plug in something that's bigger than this. I'm going to be super lazy. I'm just going to imagine plugging in a really big number. Now, if I plug in a really big number, that's really big. And that's really small. So the positive piece is big, the negative piece is small, the positive piece wins. Okay. So, from the shape of the graph, that tells me that this is a min. Now be careful, all I know is that it's a relative min. But there's a very nice fact that we have. Because there was only one critical number on this open interval, I know that this relative min is an absolute min. And I get that just from the shape of the graph. There's no way, if the function is going up as we move away from that point, that it can ever be lower. And there's no way, if the function was coming down as we approach that point, that it could ever be lower over here. Now notice, this trick only works if there's one critical number. If there's a second critical number and the function changes sign so that it comes down, again, for all I know, it's going to come down and come lower than this. But this is a neat fact. If f of x has one critical number on AB, and if f is continuous on AB. So if I've got a continuous function, which I do, and I've got just one critical number, then if the critical number is the location of a relative max or min, that max or min is absolute. Okay, excellent. So I now have verified that this is a min. Okay. Caution, it's easy to forget this step. It's easy to just find the critical number and say, that's my answer. And honestly, on every homework problem, you're going to be right. But on every homework problem, if I were to grade it and you assumed you were right here, you would lose points because you didn't prove that you had found a min, you just found a critical number. Imagine you're working and your boss says, oh, you know calculus, great, you got this project, I want you to figure out how we can maximize profit. So you say, oh, I know calculus, I can figure out maxes, mins, critical numbers. So you go home, you find the critical number, you turn it into your boss is very pleased until the next day you come in and you're fired. Because you found a critical number, but it happened to be a min. So you just taught your boss how to minimize profit when you were supposed to maximize profit. Okay. So it is very important that you check that your critical number is actually a min if you want a min, and is actually a max if you want a max. Okay. I will tell you, all of these problems are rigged. You're asked for a max when there is a max. You're asked for a min when there is a min. So if you find the correct critical number, it's going to be the location of your max or min, but you're building horrible life habits if you don't actually confirm that it's a max or a min. Okay. All right. So having confirmed this, now we want to just make sure that we actually answer the question. The question was to find the dimensions that would minimize the area. So that would be that the radius is the cube root of 1,000 over pi, and that would be centimeters. If you remember, volume was given in cubic centimeters. If volume is given in cubic centimeters, that means that all lengths will be given in centimeters. So it's got to be consistent, but the units also have to match the dimension of things. The radius is a one-dimensional measurement. And then the height, we had said that the height was 1,000 over pi r squared. So that's just going to be 1,000 over pi times the cube root of 1,000 over pi squared, and that would also be centimeters. Okay. These problems are involved enough that I'm not going to require that you simplify things like this. You can leave your answer in sort of a messy form. Realistically, You'd have a calculator if you were doing this in the real world, and you could get a decimal approximation. All right, so there's our second example.